In this example, we will illustrate how knowledge-based prediction of toxicity can be used within a multi-parameter optimization environment to guide the selection and design of compounds with a good balance of properties and reduced risk of toxicity. We will explore a library of compounds with experimental inhibition data against the cyclooxygenase 2 target, also known as COX-2, with the goal of identifying a high-quality lead series comparable with the best-in-class celecoxib, also known as Celebrex. However, we should consider that other COX-2 inhibitors, including rofecoxib, also known as Vioxx, and valdecoxib, also known as Bextra, were withdrawn from the market due to adverse events. Having started StarDrop, use the File Open menu, select the dataset COX-2 library, and click OK. This will open a dataset containing 152 compounds with potency data in the form of measured pKis against the COX-2 target. This represents a small library of compounds which have been screened for potency and from which we would like to identify a high-quality lead series. To explore the chemical diversity of this library and the distribution of potency across it, we are first going to take a look at a chemical space plot of this data, so click on the Visualization tab to the left. Click on the Chemical Space button and then click Create to create a new chemical space. In the dialog box that appears, type in a name for the chemical space plot. In this example, we're going to call it COX-2 space. We can build different types of chemical space plots based on chemical structure and/or property data, but in this case we're going to use the defaults, chemical structure only, and the visual clustering method. Click the OK button and wait until the chemical space has been created and the dialog box disappears. When the process is complete, a chemical space will be plotted in the Visualization tab. Click the Detach button to create a separate window containing this chemical space. This will allow us to keep this chemical space plot visible as we explore the library. First, we will colour the points by the experimental potency to identify the most potent chemistries. In the detached plot, click on the colour block in the key and, in the Format by Property window, select pKi from the source and click OK. In the resulting plot, we can see the clusters containing the most potent compounds, in this case coloured yellow. However, the most potent compounds are not necessarily the best starting point for a high-quality lead series. Ideally, we would like to identify a potent series that is also likely to have an appropriate balance of absorption, distribution, metabolism, and elimination properties, also known as ADME. StarDrop's probabilistic scoring approach to MPO makes it easy to identify the chemistries that are most likely to achieve the required profile. Change to the Scoring tab in StarDrop and click on the Load button to load a new scoring profile. In the Load Profile window, select the file COX-2 Scoring Profile and click Open. The scoring profile will be displayed in the Scoring tab. Click on the arrow button to calculate the score for each compound based on the experimental potency and the predicted ADME properties. The models required to predict the ADME properties in the profile will be run automatically, and the results will appear as columns in the dataset. Right-click on the COX-2 Scoring Profile column header in the dataset and select the Sort Descending menu option. The highest scoring compounds will now be at the top of the dataset. We can colour the points in the chemical space by the overall score. To do this, click on the colour block in the key of the detached plot, select COX-2 Scoring Profile from the source menu in the Format by Property window, and click OK. From this, we can see that the most potent cluster is now quite red, indicating that it is unlikely to have acceptable ADME properties. Alternative regions are highlighted in yellow and are more likely to have both good potency and good ADME properties. Note that celecoxib is one of the top scoring compounds, giving us confidence that the scoring profile is prioritizing high-quality compounds for COX-2 inhibitors. Select row 7, containing celecoxib, to highlight this compound in blue in the chemical space. Note that 2 other regions are indicated as potential regions of high-quality chemistry. So far, we have not considered the potential for toxicity, and for this we'll use the Derek Nexus module in StarDrop. Change to the Models tab, and at the bottom of the list of models, you will see the Derek Nexus branch, which you can expand by clicking the arrow adjacent to the name to see the full list of toxicity predictors provided by the Derek Nexus module. Select the carcinogenicity, genotoxicity, hepatotoxicity, and mutagenicity endpoints by checking the adjacent boxes. Click the arrow button to run these predictions. This will take a few minutes, so in this case we have skipped ahead. Scrolling the dataset to the right will enable you to see the predictions for the individual endpoints in additional columns. These correspond to structural alerts with levels of likelihood based upon precedents from experimental data. A no-report outcome for an endpoint indicates that the query compound does not contain any structural alerts associated with that endpoint, and there are no reasons based on the physical properties of the compound to predict either activity or inactivity. Other possible results, in ascending order of likelihood, are equivocal, plausible, and probable. Any alerts are highlighted in the table, and from this we can see that there is an indication of the potential for toxicity for some of the top scoring compounds. We can visualize the results in the library's chemical space. In the chemical space plot window, click on the color block in the key, as we did previously, and select hepatotoxicity from the source in the Format by Property window. In the resulting chemical space, we can see that some regions of the chemical space are highlighted as having a plausible likelihood of hepatotoxicity, including one of the high-scoring regions. Of course, we can include the toxicity predictions in a scoring profile to prioritize potent compounds with a good balance of ADME properties and a reduced risk of toxicity. Change to the Scoring tab again and click on the Load button to load a new scoring profile. In the Load Profile window, select the file COX-2 scoring profile with toxicity and click Open. The scoring profile which includes the toxicity endpoints will be displayed. Once again, click on the arrow button to calculate a score for each compound based upon the new profile. By colouring the points in the chemical space using the new score calculated with the toxicity endpoints, in the same way as we did before, we can see that there is now one region of the chemical space which contains the majority of the top scoring compounds. This indicates that this chemistry has the highest chance of providing a high-quality series. Based on these results, an appropriate strategy would be to focus experimental and synthetic resources on the highest scoring compounds. However, given the potency and good properties of some alternative areas of chemistry, these should not be rejected outright. As reflected by their scores, predictions of toxicity and other properties are not definitive, and therefore it would be appropriate to sample a small number of additional compounds for further tests to confirm the predicted hypothesis and avoid missing valuable opportunities due to uncertain data. So far, we have been considering strategies for selection of compounds, taking into account the risk of toxicity. Now we will illustrate how we can explore strategies to redesign compounds and reduce the risk of toxicity. Using the mouse, hold down the left button and draw around the cluster of compounds shown to select the corresponding compounds in the dataset. Note that one of the selected compounds is lumiracoxib. This compound has been withdrawn from the market in several countries, mostly due to hepatotoxicity concerns, and has never been approved for use in the United States. We can use StarDrop's interactive designer and the glowing molecule visualization to identify the substructures causing alerts and guide efforts to redesign compounds with a reduced risk of toxicity. Change to the Design tab and select the row containing lumiracoxib. The structure will be copied into the editor in the Design tab. In the list of predicted properties below the editor, select hepatotoxicity to highlight the structural alert for this endpoint. Now use the editor to modify the structure of the carboxymethyl. Firstly, use the eraser tool to delete the methylene. Then use the bonds tool to join the carboxyl group directly to the phenyl. With each edit, all of the predicted properties in the summary table below will update instantly, allowing all of the properties to be monitored simultaneously. We now have a compound with a lower predicted risk of hepatotoxicity. This example has used some of StarDrop's capabilities to illustrate how knowledge-based prediction of toxicity, provided by the Derek Nexus module for StarDrop, can be used in early drug discovery to reduce the risk of encountering toxicity issues downstream. To download the example files and step-by-step guidelines to try this example yourself, visit the tutorials section of the Optibrium community.